All right, students, so here we go. We're going to do a quick video, actually probably not so quick, this might be a little longer, on complete graphs and some ways to solve them. So what is a complete graph? So a complete graph is a graph when every pair of vertices is connected by a unique edge. So all of these vertices, all 5, are connected to each other. So that is a complete graph. So how many paths do we have from this complete graph, and any complete graph for that matter? So how many paths, if we start at a given vertex, how many ways can we get from New York and touch all of the other vertices just once? So this would be a Hamiltonian path. So there's an example of one, right? We could go from New York to Philadelphia, to Chicago, to Houston, to LA. That's one path. There's another one. We could go to New York, Chicago, LA, Houston, Philadelphia. Now we can go count them all, but there's an easy way to actually solve this problem. So if we think about it, if we're starting from New York, there are 4 choices we can make, right? There are 4 different cities we can go to because it's a complete graph. I can go to any of the other cities I want. So there are 4 choices from New York. So let's say we choose Philadelphia. That's our choice. Now once we've chosen Philadelphia, how many choices do we have left? 1, 2, 3. So there are 3 choices from Philadelphia. Say we go to Chicago. From Chicago, I only have 2 choices left. I can't go to New York and I can't go back to Philadelphia. So there are now 2 choices. Then from LA, there's only 1 choice. So if I multiply all those together, that's actually the number of paths that we have. So 4 times 3 times 2 times 1 is 24 different paths from New York. So there's actually 24 different ways we can travel from New York. Now here's an interesting problem. Since it's a complete graph and I have 5 different vertices, how many paths are there in all? So like if I start from Chicago or Houston or LA or Philadelphia, each of those is going to have 24 paths. So it's really 24 times 5. And oh, by the way, that notation, 4 times 3 times 2 times 1, is known as factorial. And you'll see that in class. I'll show you how to do that on your calculator. You'll see a little thing on your calculator, a little shortcut for multiplying consecutive digits in a row. So from all 5 cities, it's 5 factorial, or 120. So let's look at another problem. And this is basically how many circuits, how many Hamiltonian circuits are there on this connected graph, on this complete graph, right? All of the vertices are connected to each other. So that's an example of a circuit, right? If I start in New York, go to Philadelphia, to Chicago, to LA, to Houston, back to New York, that's a Hamiltonian circuit. I've touched all of the vertices just once, well, apart from the starting and ending point. And here's the deal with the circuit. It doesn't matter if I go frontwards or backwards, that's the same circuit, right? I could go this way or in reverse. So it's sort of like the last problem, only we're going to be double counting some things. And also the other thing is it doesn't matter where we start. I can pick any one of these points and the circuit is going to be the same, right? I can draw the same circuit starting from any of the points. So what we're going to do is instead of counting all of the different paths like we did last time, where we got 120, we're going to just start from 1. We'll start, say, from New York and count all of the paths. So say if I start from New York, there are 4 places I can go. And then I'm going to go to, say, Philadelphia, and then there are 3 places for me to go, and then 2, and then 1. But, again, by counting all of those paths, I'm double counting because I can go forwards or backwards. So really, it's this. N, meaning the number of vertices, minus 1 factorial divided by 2. So what is that? 5 minus 1 factorial is 4 factorial over 2, which is 4 times 3 times 2 times 1 divided by 2, which gets to 12. So there are actually 12 circuits here. And again, the reason is we're dividing by 2, because in our last problem, when we started from New York, we figured out that there were 24 different paths. But when we close that path, it becomes a circuit, and then all of a sudden I can go backwards. So that's why we end up just double counting half of them. So let's take a look at another example. All right, students, so here we're going to talk about the brute force algorithm, and this is actually used for weighted graphs. And here we have this weighted graph, and this is not a complete graph because B is not connected to D and A is not connected to C directly. They actually go through E, so that's not a complete graph, but that's okay. I made it a little easier this time for looking at this algorithm. And this algorithm, what it's going to tell us is the most efficient, or it could be if this is distance shortest, or if these are costs, like the lowest cost circuit in this graph. And this is known as the brute force algorithm. So here are the steps. List all the possible Hamiltonian circuits. 2, find the weight of each circuit. And 3, select the lowest. So I'm going to make a little table with circuits and weights. And let's look at one circuit, for example. We could go from A to E. And then from E, I could go to B. And then I could go to C, to D, to A. So that's one example of a circuit. So I'm going to write down the circuit right here. And how we write down a circuit is we just list the order of points in order that we visited. So that's circuit 1 that I'm visiting. Now what's the weight of that circuit? Well, 2 plus 3 plus 7 plus 6 plus 4, which is 22. Let's take a look at another example. If I go to E, I could also go to, no, I can't go to C. That's not going to work, because if I go to C, then all of a sudden I can't complete my circuit. So I really only have one other choice, which is to go to D. So if I'm going to go A to D, A to E to D, and complete that circuit, then that weight is actually 21. So that's a second example. Now there are a number of different circuits we can make. I could do A, B, E, C, D, A. And that weight is 20. Or I could do this one. A, B, C, E, D, A, and that's 19. Now I could keep going. There are a number of different circuits I could make, and we could just try and figure out all of the circuits we can get, and fortunately I made a list of that for us, so we'll take a look at that. Here's the list. So these are all of the circuits that I can make. Now notice, these two have the same measure, the same length, or whatever that cost is. But notice these circuits here, right? So A, B, C, E, D, A, which is this circuit, is actually the same as this circuit, A, D, E, C, B, A. A, D, E, C, B, A. So see, I've just double counted the circuits. So I've actually there are really only 4 different circuits here. I just did them twice, once frontwards and once backwards. So that's going to happen with this brute force algorithm. That's why it's a little tedious, is because you end up basically double counting everything. So the easiest way to check is to see if they have the same value. Now it's not necessarily going to be the same circuit if they have the same value, but sometimes it will be. So you just have to check the order of the points. And again, it doesn't matter which point we started with, right? So if we started with E, we could have come up with the same 4 circuits from E. They've just been listed in a different order. So like, it would have been like EDA, so EDA, B, C, E. So you can see that EDA, B, C, E, right? So it's really the same circuit. Okay, so we're going to look at one more algorithm here, and this is known as the nearest neighbor algorithm. And how does this work? Well, basically, what we're going to do is we're going to select a starting point, then select each edge with the lowest weight, and you repeat until the circuit is complete. Now this is known as a heuristic method. It's not necessarily going to give you the best outcome, but as you can imagine, as these graphs get bigger and bigger and bigger, there's just going to be so many different combinations that would take you forever to use the brute force method. So this is just an approach to find a solution, not necessarily the best solution. So let's take a look. If I'm starting here at A, the shortest distance is this 2, so I'm going to go to E. Now, I can't go to C because then I can't close the circuit there. I could go to B, which is 3, or D, which is 1. So I'm going to go to D. And then I can't go this way because then I can't complete my circuit. So I have to go this way. And then I'm going to just go ahead and close the circuit. So what turns out to be the nearest neighbor algorithm solution is this one, which is, again, not the most efficient or the shortest path. So it's just the most efficient. Not the most efficient, it's just a solution. So let's look at this example. So this will be an example of why it gets so much more complicated in using, let's say, like the brute force method as you add complexity to the graphs. So this is a complete graph. What you are tasked to do right now, and you can pause the video, is figure out how many circuits are there from this path. The second part to this question is what is the cost using the nearest neighbor algorithm from New York? So here's the solution. So notice we have 12 different paths. So there's 12 different circuits, I should say, not a path, 12 circuits from New York, or from any city that is. Because if I start in Chicago, I have 4 choices. Then wherever I go, I have 3 choices, and then 2, and then 1. But remember, if I start in Chicago and I have a closed circuit, wherever I end up, I'm going to end up back where I was. So it doesn't matter if I go forwards or backwards. So that's why we're dividing by 2. Now, what is the cost using nearest neighbor algorithm? And I'm not sure if this is the most efficient, but here's nearest neighbor algorithm. So if I start in Chicago, I could go to New York. That's 70. That's cheaper than 100 or 170 or 150, so that's what I'm going to do. Sorry, I started in New York. I'm going to Chicago. And then Chicago to Houston. And then Houston to LA. These are my cheapest alternatives. I'm not using any of these inside ones because they seemed a little more expensive. So there's my path. And what's the cost of all that? You can add it all up, and you get $450. So that is the cost using the nearest neighbor algorithm. I hope this helps. Please let me know if you have any questions. And again, I think that might be the most efficient path for this particular task. Thanks.